Dr. Benjamin, good day. Sunil, good day. It's Chidozie Eloka, and this is my recording video for the UAV data acquisition project. The project started last semester and is just coming to an end. So I wanted to give a brief walkthrough of everything that's been done, how the system works, how we use the test bed to acquire data from the encoder, do the conversions required, and generate the trajectory map. So the first thing that was done was the stepper.h function. This actually collects the binary values that are coming out of the encoder. So the encoders are connected on the circuit, as you can see, hooked up with the clock and the counter. So on each revolution of the encoder, the counter increments itself. What happens is there's going to be data overflow from the counters, and because of that I had to implement a function in here to keep track of that count. That's this position function. It keeps track of the count of all the counters, and that way we don't lose any of the steps of the encoder. So we have the three counters, J3, J2, and J1, and these are the 8 bits respectively that come out of each of them. Each counter, or each joint rather, has its position, it has its last value, and it has its current angle. So that's the same for all joints. Then we have a reset function. So during the design of this project, additional functionality had to be added. I needed to be able to increment the counters by 30 degrees to actually check the correlation between the steps I was receiving and the binary value changes. So I added extra control features that can still be added if need be, but presently are disconnected. So we reset the value, we have the up and down counts, we have activate, and then we have an I increment. So this I increment was a safety feature that was used to shut off power to the circuit. So whenever the circuit was inactive, this count would start immediately, and if the count finished before the next activity pulse, it would shut down all the motors and cut off power supply to the circuit. That doesn't really interfere with any test being performed, because once a joint moves, power is immediately restored to the circuit. So it's just like a safety mechanism so that the circuit isn't left idle and actively powered while nothing is being done. So these convert the values, and we have all the logic in here. This bit was used for the stepper motor controls for direct increments, and then we have the read binary string, and with all the conversions, with all the mathematics. The functions that perform the calculations are shown in the appendix section. At the end of the day, we have our output from the serial monitor. We have J3 on the leftmost string, we have J2 in the center, and we have J1 on the right. So if you look at the video shown in the screen right now, you're going to see that when I move the test bed, when I move the test bed to the right, so this is J1 being incremented. You see the changes in J1. If you move J1 by itself, left or right, you're going to see the resulting changes in J1, and when it crosses 0, which is the original position, it will go from 0 to 360 or 360 back to 0, and you can move. So if you look closely, you're going to see that we have stoppers implemented there so that the joint can go more than 270 degrees in total. So a fine feature I put for being able to track the drone easily was centering it right on 0. So after hooking up the circuit and fine-tuning the 3D print, this is the SolidWorks drawing for the test bed, so you can see the full range of motion in here. So the arm is very solid, it's very rigid as per requested. The new things in this design, the new features we have are the integrated stoppers. So we have the stoppers 90 degrees and 0. Then we have the 270 degree stoppers for the J1 revolution. We have the encoder mount. Then we have the 90 degree limit for J3. Then we have the drone mount as well. So this is the encoder mount for J2. Then the encoder mount for J3, sorry. So the next important thing was the graphical user interface. So this was written in MATLAB. When we get in data from the Arduino, we run that into MATLAB through the serial monitor. As you can see here, we are going to create values on the serial monitor, and what MATLAB does is it goes into the serial monitor and grabs these values, and that's how we perform the calculation. I used a function created by Peter Cork. He created a function that does trajectory mapping for robotics systems. So it's a robotics toolbox release, and it does most of the calculations, the forward and inverse kinematics for the robot. So the code is attached to the final report I submitted, and in the appendix section the full program used to run this is available. It's also attached to the email that's been sent out with the demonstration video. So if we run this, this is the GUI we have. I tried to make the GUI as user friendly as possible. I didn't want it to look too complicated. I wanted a very simple layout. So we have on the right side, we have the position map. This is going to show the trajectory of the drone. Then we have the velocity map, and we have the acceleration map. So it's going to give you the individual components of velocity, that's in X, Y, and Z, the individual components of acceleration X, Y, and Z as well. So this J1, J2, and J3 are the angular position of the UAV during flight. And then the pose X, Y, and Z are the Cartesian coordinates. So you can actually put in a value. You can say, for instance, if you started your drone at 0, 0, and 30, where would that be in 3 space? If you calculated the forward, it would show you where that is in 3 dimension. You can delete the current map you have. It's going to clean everything. You can clear the log. It will clear the event log. We can record our flight, playback. You can save your map. You can open your map. So before that, we have the test bed parameters. Before you run any test, before the operator runs any test using this test bed, you first need to set in the joint length. So these are already set automatically from my design. If a new test bed were to be used with this GUI, the user would have to change these values to whatever the joint length of the new test bed is. So for the test bed we designed for this project, it's 24 for J1. That's the length of J1 from the testing table. Then the length of J2 is 18 inches, as you'll see in the schematic sketches, and the length of J3 is 6 inches. The actual test bed weight is about 0.5 kilograms. So this is changed to this is 0.5 kilograms in lbm, in pound mass. Then we have the UAV weight as 2.2 pounds, which is roughly 1 kilogram. So if a different drone is being used, the UAV weight would have to be changed, and if a different test bed is being used, the test bed weight is going to be changed. The last parameter you need to assure yourself of is the Arduino serial port. The program would fail if you put in the wrong serial port for the Arduino. Once all these are set, you can select record flight. Once the drone is done with its flight, you set it back to the initial position. When you hit playback, you're going to see the position figure go through the range of motion that the drone went through. So you can rotate the plot if you would like to get different views. You could change the view as you want, and that just gives you convenience. So the total flight time was 17 seconds, and once this is complete, it would show you that it's complete. The playback is complete, so you need to release the playback button. And once you release that, it will tell you playback finished, and it will give you your velocity plot and your acceleration plot, as well as your final position on here. So an interesting thing you can do is you can play back as many times as you want. If you decide to play back, you could pause at any time, and it will give you the velocity up until that point in time. You have your velocity map and acceleration map again, and then you have the instantaneous position of the drone at that point. You have the thrust being generated at that point, and the velocities component and acceleration components at that point in time as well. So you could play back and pause as many times as you want, and you will get these values as we move on. So after the playback, you could decide to save the map, and all you need to do is save this. It has to be saved in .xlsx format. If you saved it, if you try to do this, for instance, .csv, it will tell you it's an incorrect file extension, and it won't let you save. It's only saved as Excel, and let's call this UAV. So it's going to take a few seconds, but once it saves, it will tell you on the event log that the file was saved successfully, or there was a problem saving the file. Okay, so the file has been saved successfully. You could open the map in here and replay everything that happened, but before that, I'm going to go into my working directory and open the Excel file that was saved. So if you put in the working directory, you're going to see UAV, and if we open that, so it takes a while to save because the file is huge. It runs at the clock rate of the Arduino, and every millisecond counts. You're going to have an infinite number of data points. As you can see from this 17-second test we ran, we have nearly 6,000 data points, 6,000 values of thrust, velocity, acceleration, and position. So interestingly, with the angles that are saved, positions, velocity, acceleration, you're going to have time-stamped values. So back to the function, or back to the GUI, you can delete the map. Tells you map deleted, and if you try to play back, file not found, you wouldn't be able to play back. You can always record. Here we're going to open, or we're going to try to open UAV. So if you try to open the UAV file, so if it opens, it will tell you file opened successfully, map updated, and you can hit the playback button once again. Another interesting feature is that you can increase the speed of the playback. You can make it twice as fast, for instance. So if you remove the map, you want to play 4 times as fast. Could do that as well. And again, you get your plots. So that's all I have. The project was very exciting. I apologize for the unbelievable delay, the nearly semester long delay in delivering this project. I had taken on more work than I could handle at a given point. I apologize in advance for any inconvenience the late submission of this project might have caused. I put in a lot of work, put in a lot of effort, tried to get things done as perfectly as possible, because I think perfection is really key. I wasn't going to turn in a project that was rushed. I rushed it anyway, but I made sure everything was done as perfectly as could be. I've attached all the supplemental documents, all the necessary files, everything that's going to be needed for anyone who wants to use this project. That's the test bed or the GUI for anyone who wants to improve the project. The wiring diagrams are in there. The SolidWorks files are attached as well. The whole methodology, the programming concepts, everything is attached to the submission link. Thank you very much. I really appreciate you giving me this project. I learned a lot in the nearly year-long work that was done on this. It was a pleasure working with Sunil. It was a pleasure working with you as well, and the ECE department. Thank you very much.